And then the first part of this is going to be a review. So what I was thinking of is just starting with chapter 22 and just kind of going through it in that sequence, so that you can stop me when you have any questions. Is that a good idea? Or does anybody have any questions that they want to ask straight out? No? Okay, well, let's share the screen for chapter 22. So anyway, the first one was about just, organic compounds in general. And then naming alkanes, alkenes, alkynes, alkyl halides, and some aromatics. So remember, every time you look at a functional group, there's naming, there's the physical properties, and then there's the chemical properties. And so the physical properties are really based upon all that review stuff. First couple of chapters I put in there that were really not part of this course. I think it was chapters 10 and 14, maybe part of 16, I think. So, naming hydrocarbons, you should know at least methane through decane. There is another system that keeps going, undecane, dodecane, all that stuff. And if I take an alkane, where there's 4 bonds for every carbon, and I take off a hydrogen, it's now called an alkyl group. So methane becomes methyl, decane becomes decyl, because now this can bond to something else, right? And then in addition to the straight chain ones, which are called normal or N, we have isopropyl, isobutyl, and iso really means split on the end. And the other thing about the nomenclature is that the root of the word of the name is the longest continuous chain, but when it comes to isopropyl, it is not the longest continuous chain, it's the total number of carbons. Same with isobutyl, same with sec-butyl, and same with tert-butyl. So let's see, just to give you some example names here, right? I don't think people have a problem with this part yet, so I'm not going to spend a lot of time on it. Cyclic alkanes, we do have a couple of different nuances. One is you don't get free rotation about single bonds, so therefore this right here is different than this one right here. Okay.
I don't know if I have a model to show that.
Come up with one. So this one, you see that you can't rotate it in 180 degrees. If it was, a linear one, yes, you can rotate it 180 degrees, so no problem. There is no cis-trans isomers. But what you do if you have a model is you make the model perfectly flat. And if you have the 2 odd substituents on the same side of this plane right here, either that way or that way, that means that they're cis. But you got to have the ring flat, because I can make it look trans if I go like this. I pucker the ring. If the ring is flat, I can see that those 2 green ones are cis to each other. To turn it into trans, I would have to break a bond, reform it. So therefore, these are in fact different molecules. So you need To depict a three-dimensional object on a two-dimensional surface, we use these wedges and I'd say the hashed wedges. So this one is coming into your face. This is going out away from your face. So these are opposite. So that would be trans, right? This is the same. So it would be cis. And the only other thing about it is that you have to get the lowest numbering system. So for example, 1, 2 is different in the lowest numbering system than 1, 2, 3, 4, 5, 6. So we use 1, 2, not 1, 6. And all the substituents are in alphabetical order. Naming alkyl halides. The alkyl halides, the halide itself doesn't qualify as a functional group, so it's just named as a substituent. So notice that this one right here is cyclohexane. It's got a methyl group on it, and it's got a chloro group on it. And so we put them into alphabetical order. Chloro comes before methyl. Then the numbering system would be 1, 2, 3. So instead of saying 3, 1, it's better to say 1, 3. So the numbers are increasing. Then this one shows you stereochemistry. So these guys are opposite, so they're going to be trans.
I have a question. You mentioned functional groups and substituents. What's the difference between those two words?
Well, right now, these don't have a functional group. But for the sake of naming, then the cyclohexane is the root, right? So then a substituent is anything that's sticking onto that. So chloro is a substituent, and methyl is a substituent. When we get to alcohols and things like that, then those are the functional groups. You're going to give priority to the hydroxy group because you're going to name it as an alcohol. So that alcohol then becomes a functional group. It's kind of confusing because in a real organic chemistry course, there would be a chapter on alkyl halides, and we treat them as a functional group. But when it comes to naming, we don't treat them as a functional group. So with more complex ones, like here's the longest continuous chain, okay, which is this right here. But then what do we do with this one? So it's a methyl group, but it's also substituted with 2 fluorines. So we just put the whole thing in parentheses. Okay? The whole thing goes in parentheses. If you didn't put it in parentheses, then you'd be confused. Are these 2 fluoros the same as those? Or are they different? The physical properties are simply that they're nonpolar. There is no polar covalent bond, so they only have London's attractions and nothing else. When it comes to the alkyl halides, their physical properties, some of them are polar or slightly polar, and at least iodine is totally nonpolar. Okay. So this one right here is not symmetrical. And this is a polar covalent bond. So this would be a polar molecule. This one, on the other hand, is perfectly symmetrical, so it would be a nonpolar molecule. So I just gave you some examples of some compounds that are chlorinated. And then we looked at the chemical properties of alkanes. So one of them is that they burn, they're combustible. And I put in the case of insufficient oxygen, or you might get some carbon monoxide, but you should be able to balance these reactions in the situation where there's plenty of oxygen around. So the products will be carbon dioxide and water. Same two things that come out of your mouth and nose. And then we also have aliphatic substitution. So I'm not going to ask you any questions about the catalysts. In nature, there's lots of halogenated compounds in nature, particularly in marine seaweeds, and those are all done by enzymes. So they're not random like with light. Okay. I know some students had asked about, well, what is the difference between monosubstitution and polysubstitution? Well, if you do it in a test tube, most likely you're going to get all different kinds of products because you can't really control it very well. If you do it in a cell, then the cell is going to control the reaction by enzymes. You won't have extra products. So I would concentrate on, monosubstitution, but what's important about the polysubstitution is that you now realize that the hydrogens on this carbon are different than the hydrogens on this carbon. Okay, so that's something that you should recognize. The ring opening reactions is really only important for 3-membered and 4-membered rings. Then alkenes. So we already know about cis and trans. So I'm looking at this one, and how come the name doesn't have cis or trans in it? It's because the criteria to be cis or trans is you go to each of the carbons in the double bonds, and each one of those has to have different things bonded to it. So this has a hydrogen, and it has this big other thing over here. This has 2 hydrogens, so it does not have geometric isomers. So this one, I look at this carbon, here's the big one. Then I look at this carbon, here's the big one. So the big ones are on opposite sides, they're trans to each other, so that's where we get the name.
I have a question regarding the test quiz that you sent.
Yeah.
So in all of the examples in your notes, you're comparing 2 different substituents that are the same. But in the quiz, it looks like we're kind of comparing 2 different substituents. Like one is CH3 and one is CH3. Can you kind of go over that a little bit?
It doesn't matter, because the criteria is simply you go to one carbon in the double bond. These 2 have to be different. You go to the other one, they have to be different. Now this happens to be the same as this, but that's just happenstance. Does that make sense?
So you're just going to take the biggest on each side of the double bond. Doesn't matter if they're the same or not.
Right, exactly.
Okay.
Right. And I won't be asking you about the E and Z system, but I think it's good for you to know what it is. Then yeah, the trans is a little bit more stable when it comes to equilibrium. That's the reason why retinol works the way it does. So if you look at, where's the part where light comes in now? Okay, right here. So here we see it's cis 1112, right? That's cis. There's a hydrogen here, there's a methyl group here, there's steric hindrance right here. They're trying to occupy the same space. So this has a higher potential energy than does the all trans molecule. That's why if you give it light, these electrons right here absorb the light. You see it's a conjugated system. It absorbs the light. The electrons are then activated and could go through a chemical reaction. So the light is causing this to go up to the transition state. So then it could come down this way and give off energy or go back to where it started. And here is isoprene. Notice with isoprene, we don't say cis-trans because look at this double bond. That carbon has two things that are the same. Same thing with this one over here. And when we name dienes and trienes, you're naming it as, say, a diene. That means that the functional group, which is now the double bonds, both of those functional groups have to be in the longest continuous chain because you're naming it as a diene.
Sorry, with the dienes and trienes, does that just mean that there's like multiple double bonds?
Exactly, right.
Okay.
Mhm. And so say we're looking at this molecule right here. Here's the functional group. It's an alkene. We have to name it as an alkene. So I got 1, 2, 3, 4, 5, 6, 7, 8 in a row. So cyclooctane becomes cyclooctene. Then with the numbering systems, because it's named as a double bond molecule, carbons 1 and 2 have to be the double bonds. So the numbering system would be 1, 2, so that makes this a 3 to give it its lowest number. So here you see that this is trans. So the trans has to do with the substituents, right? It's kind of understood that this would have to be cis. That would have to be cis, otherwise the ring could not form.
In those two cyclopentenes, how come you don't say ortho or use like the ortho meta?
Oh, that's only for benzene,
Okay.
for the benzene ring. And with alkynes, there is no cis-trans isomers. There's no geometric isomers. So if you look at this compound here, here's the functional group. It's an alkyne. I have to name it as the alkyne, so the alkyne has to be in the longest continuous chain. So your choices would be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So it's got to be hexyne, right? And where is the triple bond? On carbon number 1. So 1 hexyne covers all of this, which is the same as all of this. Doesn't matter which way you go. And then on this, if I do this as my longest continuous chain, then my substituents are a methyl group and a propyl group. And they're both on carbon number 3. So here I'm just talking about conjugated systems. And you should know the bond angles, by the way. Here's what a conjugated system looks like. We saw that also, like beta carotene, if you take an enzyme and cut it in half here and you oxidize it to an aldehyde, that is this molecule right here, vitamin A. So nutritionally and health-wise, does that mean that if you eat carrots, you're automatically going to have good eyesight? Apparently not, right? Something to keep in mind. So then we get to the chemical properties of unsaturated hydrocarbons. That means they have either a double bond or a triple bond. you have addition reactions. So I put them into two different categories. What you're adding is symmetrical, like with hydrogen. So it doesn't matter which goes to which, you get the same product. Same thing with reduction of alkynes. Alkynes in general will just simply go all the way to alkenes. It was a really important finding to be able to stop it at forming the alkene. That way they could prove that alkynes and alkenes are related to each other just by saturation. So halogenation is another one that's symmetrical. It doesn't matter which bromine, for example, goes to which carbon. Then we look at asymmetrical reagents, for example, hydrogen bromide. Then the hydrogen could go to either carbon, but one of them is going to be the major product and one is going to be the minor product. So Markovnikov's rule applies, so the rich get richer. So that green carbon right there has 2 carbons. This black one right here has only 1. We don't count all this. The reason being is that hydrocarbons are unreactive. This is reactive, this is not reactive. So when the rich get richer, this would be your major product. So same with alkynes. You simply apply Markovnikov's rule twice. Then I went into carbocation chemistry just a little bit because I want you to know that we do have mechanisms, and the mechanisms help us understand how certain products are formed and others are not. So in this particular example, methyl groups or carbons are able to donate electrons to help alleviate the magnitude of that positive charge. Here is a secondary carbocation. I got 2 carbons that can, what we say, hyperconjugate with the carbon, which really means overlapping p orbitals, what it means. And here I have only 1. So this is more reactive. This is more stable. And so it becomes a rate situation. They're not that much different in terms of energy, but if I keep the temperature low enough that I don't form this one, I direct the reaction towards going through the secondary carbocation, and that will give me the major product. So we have hydrogenation. So you should think of water like this. So the rich get richer. And then I went through a free radical mechanism for polymerization of alkenes. So that's one way that polymerization occurs. That's probably the predominant way. But they can also be done through carbocation mechanisms. But what you really need to be able to do is, if I give you the monomer, notice it's got 2 carbons in the double bond, right? And I ask you to draw, say, the heptamer. 7 times 2 means that there should be 14 carbons in a row. And it's no mystery. On the first one that I started with, there's the hydrogen there. And over here, it's the chloro. And the hydrogen and the chloro just repeats itself. And you should also be able to take a stretch of the polymer, whatever it is, and because you know it came from an alkene, there's 2 carbons right here. Whether you take it this way or whether you take it this way, you get the same thing. That was the monomer. All you have to do is pull it out of there and put the double bond in there. The rubber is more complicated, so I just put it in the red box. Okay. So ozonolysis is the way to break the double bond. And so ozone gets inserted between the carbons right here. And the product is oxygen, because ozone is more reactive than oxygen, right? Even though oxygen is still reactive. So all you're really doing is you're breaking that double bond, one bond at a time, through a long mechanism, and you end up with an aldehyde or a ketone. So you could get 2 aldehydes, you could get 2 ketones, it doesn't matter. All you do is you cut that double bond in half, put an oxygen on each entity. That's all you're doing. And with aromatic compounds, we described benzene and why we have resonance structures and why the benzene ring is so stable because of resonance stabilization energy. And here we're getting a better idea about the delocalized electrons that allow for the absorption of light. So delocalized electrons is what we mean by putting this double, single, double, single, double, single. Each carbon right here has a p orbital left over that way, another one that way, and those p orbitals then overlap. They start sharing electron clouds. Okay. So this is a conjugated system. So does benzene absorb light? Yes, it does in the UV range. Here is, oh well, somewhere. Here's beta carotene. It's a conjugated system, right? It absorbs light in the visible range. It does not absorb orange, but it absorbs all the other colors of visible light, so therefore it has color. Whereas benzene absorbs only the UV light, so it doesn't have color that we can see. So then, at this point, we should know toluene and phenol from the next chapter. And chapter 25 will look at amino groups. So then we'd have to know that for unit 2. Right now, these are the only ones for unit 1. And then this is the case where you can use ortho, meta, and para. So before the numbering system became prevalent, they used ortho, meta, and para, because the molecules that they're dealing with were not more complex, they were more simple than this. So ortho, meta, and para worked fine. So ortho, meta, and para also works for position. So if I look at naphthalene, right? If I have a chlorine, say on carbons 1 and 2, then they are ortho to each other. If it's 1 and 3, then they're meta to each other. If they're 1 and 4, then they're para to each other. So biphenyl and naphthalene are polyaromatic hydrocarbons. So there's a whole bunch of them. Many of these are made by plants. I've seen these in plants. They're also, when you burn coal and stuff like that without very much oxygen, you'll get some of these sooty type products formed. And the properties, the physical properties of aromatics are similar to the hydrocarbons. Only London's attractions are possible. Then you can get benzene to burn. You can get benzene to do, what's the word for it? Addition reactions, but only under extreme conditions because the benzene ring is so stable. But it is quite easy to do substitution reactions. So you're just simply taking a hydrogen and substituting it with something else. So here, I'm substituting it with a chlorine, so then I have a hydrogen and a chlorine left over. Here, I'm substituting the hydrogen with an ethyl group, and I have a small molecule left over. Here is my small molecule. I take the hydrogen and I form hydrogen bromide again, and I'm adding this group to it. Okay. The nitration, if you think of nitric acid like this, then you can see that you're just forming water. Okay. And then the nitrogen needs another bond, and so does that carbon. Sometimes they show you this, and what they're trying to do here is show you what's called formal charges. So nitrogen, in this depiction right here, they're not showing you the bonding. They're saying, oh, this is simply the nitro group, so it's nitrobenzene. But here, when they try to show you the bonding, they're showing you formal charges because nitrogen wants to form 3 bonds, but is forming 4. Oxygen wants to form 2 bonds, but is forming only 1. So to compensate for that, oftentimes they will use formal charges. Notice that the net charge is 0, just like over here. But I'm not going to ask you to do formal charges. And then finally, sulfonation, you can think of sulfuric acid like this. So again, you're making water. So if I'm making water over here, that sulfur needs a new bond and that carbon needs a new bond. So you just give it to them. And then oftentimes you will see in the literature, including the internet, stuff like this. And I get upset when I see that because why are they doing that? There's really no reason to do that. You're violating the octet rule for sulfur. Anyway, so any other questions on that chapter?
Would you mind drawing a couple of structures from the name? I feel like I'm pretty good at naming a structure, but going the opposite way is a little bit more challenging. Would you do like a couple examples?
For what, like alkenes or something?
Yeah, alkenes, or even if you want to go into the next chapter, alcohols is fine too.
Okay. Let's do some alkenes. Hey, I don't like yellow. Let's just make it wild over there. Okay, so it's going to be named as an alkene. So I got 1, 2, 3, 4, 5, 6, 7, 8 in a row. So it's going to be called octene. Then I give it the lowest number for the double bond because notice I'm naming it as an alkene. So this was my longest continuous chain. So that means my choices for naming that are 1, 2, 3, or 1, 2, 3, 4, 5. So 3 gives me the lowest name. So 1 octene includes all of this. It doesn't include that. So that's a methyl group. It's a substituent. And what carbon is it on? It's on carbon number 4. So it's 4-methyl 3-octene. So now, the way I wrote it, I didn't write it like this. If I wrote it like that, there's no stereochemistry. But because I wrote it like this, there is a stereochemistry. So I'm looking at this carbon right here. Here's the big one. And when I look at this carbon right here, here's the big one. So I can see that the big ones are cis to each other, right? They're on the same side. So this is cis 4-methyl-3-octene. Does that help?
It does. I meant more if you give us the name, like what is your thought process and like how to draw it, like given the name.
Oh, okay. So say, let's just take this one. So I see I have octene, right? So 1, 2, 3, 4, 5, 6, 7, 8. So it's on number 3. So 1, 2, 3. So here's this, right? Then 1, 2, 3, 4. There's a methyl group. Okay. So now I took care of everything except for the cis. So the way to do the cis is like I would maybe move this down here. And then pretend like that is of this form right here. Does that make sense?
Yeah, that
Could
makes
we
sense.
could we also do like the wedges or is that different?
No, the wedges are not used right here. The wedges would be either on a cyclic compound or in chapter 24, we were looking at, what's the word? Enantiomers, right? Those kind of stereoisomers. So we didn't use any wedges in this whole chapter. Oh yeah, we did. Sorry. So if you have cyclic compounds like this, and notice that if I go like this, everything is flat. The benzene ring is flat. But these, cyclohexane is not. So if I put a methyl there and say another methyl there, then those are trans to each other. Okay? But with benzene, we don't do cis and trans because everything is flat. Does that make sense?
Yes, thank you.
Yeah.
Should I start the next chapter then? What are you doing? Okay. So now we have the functional groups of alcohols, ethers, and thiols. So naming alcohols, for example, let's just do this one, right? So I got an alcohol group. So that alcohol has to be in the longest continuous chain because we're naming it as an alcohol. So your choices would be 1, 2, 3, 4, or 1, 2, 3, 4, 5, right? So this is my longest continuous chain, so it's pentanol. And 1 would be the lowest numbering system. So that sets that. 1 pentanol would be this. Then the substituent would be the ethyl group on carbon number 2. So by the way, if I'm looking at this molecule, are there stereoisomers of it? I look at that carbon right there. It has 4 things bonded to it, but the 2 hydrogens are the same. So the answer is it does not have stereoisomers.
For that one you just went over, what if there was a double bond or a triple bond on the alcohol? Or around, I mean, not on the alcohol, but like in the carbon chain.
Okay, well, I'm not going to give that to you, but if there was, then you're naming it as an alcohol. That's the primary functional group, right? It gets precedence over the alkene. So I would put 1-pentene and then all.
Oh, okay.
And then I would have to figure out a way to get the number of the carbon where the double bond is at. So in that case, I might make it in the 1 in front of the all, like how I did here. So that would tell you where the alcohol is. And then I would put a number over here that tells you where the double bond is, because that would be then called ene, right?
Okay.
It'd be pent. Say if I put a double bond here, right? 1, 2, 3, 4. So it'd be pent 4 ene 1 all. Be one way to do it.
Okay, thank you.
Mhm. So this one, if you compare these 2 right here, so methanol, and there's a cyclohexyl group on it, right? And I didn't have to give a number where it is because there's only 1 carbon. And I didn't have to put it in parentheses because it's simply a cyclohexyl group. But over here, I had to give it a number because it could be on carbon number 1 or it could have been on carbon number 2. And then I had to use the parentheses because it's not just cyclohexyl, it's substituted as well. So the substituent is substituted. So that whole thing has to go in the parentheses. Naming diols and triols, then you're naming them as a diol. So you have to say where the 2 alcohol groups are. So for example, here's 1,2-propane diol, right? Could you not have also a 1,3-propane diol? You could have a 1,1-propane diol. You could have a 2,2-propane diol. Let's see. And the physical properties of the alcohol group is that they are polar bonds. Carbon to oxygen is polar, but especially the oxygen to hydrogen is polar. So they can form all kinds of hydrogen bonds. So again, you need to know how to draw a hydrogen bond. And I will show you that. Okay, there we go. So let's do, I don't know, something simple. So here's 1-propanol. Okay. So if I were to put partial charges on that, this would be the partial positive because electrons are being pulled that way because of electronegativity. And then instead of putting the partial negative on there, which represents really what we think of as being the nucleus, I'm going to put it out here on that non-binding electron pair. And then it could easily have been out there. So now I can see that on the alcohol functional group, I have 3 places that could attract other polar substances. Let's see, what's a good color? So say we were going to hydrogen bond this alcohol with, say, methanol. methanol is this, right? So here would be my partial positive, here would be my partial negatives, right? So this partial positive would attract the partial negative. That would be a non-binding electron pair on the oxygen. So here's the OH of one, right, in red, and in blue is the O of the other one. So that does meet the criteria for being a hydrogen bond. So what are the attractive forces between propanol and methanol? Well, they can do London's attractions if they bump into each other, just like all molecules can. There's a dipole and a dipole attractions, but it also meets the criteria for being a hydrogen bond. Does it meet the criteria for being an ion to dipole? The answer is no, because there's no ion. An example of an ion to dipole would be like this, right? So here's the ion, here's the dipole. Anyway, so what if you were instructed to draw all of the attractive forces between these two molecules? So that partial negative would attract the partial positive, and of the methanol, that would be the hydrogen. So there's another hydrogen bond. And this one will also attract the partial positive, which would be the hydrogen. So that would be another hydrogen bond. So we see that alcohols can form up to 3 hydrogen bonds with each other. That's a max. Would it really do that in the liquid phase where you have, you know, a higher temperature? Probably not, maybe half of that. If you were to vaporize that, then there would be no attractive forces. If you were to freeze it, then you would maximize the number of attractive forces. So there might be 3, actually. Any questions on that? Drawing hydrogen bonds is important. And later on, I'll tell you this. If you ever taken another biochemistry exam or another course, and they ask you any kind of a question about explain why this does this or why it does that, here's 2 things that you can use to bullshit your way through almost anything. One of them is hydrogen bonding, and the other one is conformational changes. So if you know what those are, that may help you in a situation on another course. For some reason, as soon as you start talking about conformational changes or hydrogen bonding, who's ever reading is like, oh, these people must know what they're talking about. You know? Okay, Andrea, I'll get to you after, okay? So let's see, where are we again? So with the homologous series, what I'm trying to do is show you that in these smaller alcohols, the hydroxy group is extremely important, and the nonpolar part is not that important. But as you get bigger and bigger molecules, you can see that, yeah, okay, here we have an insoluble liquid. We do have this part that should be soluble in water, but this whole other major part of it is not. This is all nonpolar. And the more we put hydroxy groups on it, the more it will dissolve in water. And to understand the chemical properties of alcohols, we really need to focus on, or be ready to focus on, what kind of alcohols are they? Primary, secondary, or tertiary. So tertiary alcohol, that carbon that contains the alcohol group is bonded to 1, 2, 3 other carbons. So when you deal with the chemical properties, it's kind of a combination of things that I'm showing you to help figure out what's going to happen, that are kind of related to mechanism, but not really a mechanism, versus memorization of what things are possible. So if you were to see this on the exam, there's only the alcohol. There is no other thing that can bond somehow with it or take something off. So it has to happen internally. So you have to remember that you're going to remove water. It's a dehydration. So that hydrogen acts as a catalyst because it jumps on here and makes it into H3O, H2O, with a positive charge, which makes it much easier to come off as water. Now you really leave a carbocation right there, and those electrons right here swing in right there to form that double bond. Okay. Anyway, that's mechanism. All you really need to know how to do is like, okay, what's going to happen? You're going to remove water. So I'm either going to get this or I'm going to get this. If I'm asked which one is going to be the major product, then I have to use Seycheff's rule, which is the exact opposite of Markovnikov's rule. So the poor get poorer. So this, say this is gone already. This carbon has 3 hydrogens. This carbon has only 2. So this is the poor one. It's going to get poorer. That means that water is taken from those 2 rather than these 2, predominantly. Then we have an intermolecular dehydration. So now you're looking at this, right? Well, what will 2 alcohols do in the presence of an acid? So the hydrogen jumps on one of these, makes it easier to form water. Now that oxygen needs another bond, that carbon needs another bond. You just got to give it to them and you end up getting an ether. An oxidation is you're removing hydrogen atoms. So here's a primary alcohol. If you see this on the exam, what does X want to do? Form XH2. So it's going to take hydrogens from the functional group and from something else. It's going to take it from here. It's not going to take it from the methyl group because the methyl group is stable, right? It's nonpolar. So if I take these off and I make carbon get its 4 bonds and oxygen get its 2 bonds, I end up with an aldehyde. Secondary alcohol, it's going to take those 2 hydrogens, you're going to end up with a ketone. Tertiary alcohol, here's my hydrogen I can take off, but I don't have a hydrogen here. I don't have a hydrogen anywhere else to take off. And XH is not going to form. It's not stable. So there would be no reaction. Tertiary alcohols are not oxidized.
I got a question.
Yeah, what's your question? Hello?
I got a question.
Mhm.
On 14 oxidation, has NAD +1 and NADP +1 and FMN.
Yeah, where did I have that? Up here? Yeah, over here?
Yeah. Can you explain to me why FMN has only the H2 is connected and the other 2 is plus H? or H plus?
Well, we'd have to look at the actual structures to see how that happens.
Okay, so is that not going to be on an exam?
No,
Or is
this is not like a bioorganic course. Yeah.
Okay,
No.
okay, okay. Thank
Just know
you.
that these axes is X and these act as XH2.
Oh, okay, sounds good.
Yeah. Mhm.
Thank you.
Okay, then naming ethers. So ethers are similar to the alkyl halides when it comes to naming. They don't get the status of being a functional group. Okay. So anyway, like this is a good example right here. And it almost seems like too much work. But what you have to do is figure out which one is the longest continuous chain, right? It's either going to be 1 or 2. So we name it as the longest continuous chain, so that would be ethane, right? And then instead of saying methyl ethane, we have to say methoxyethane. This is meth, oxy, whatever this happens to be. It's like this would be oxy Ralph. Okay. So dioxanes, we don't have to name, all of this know what a dioxane is in a relative sense. Then ethers, they cannot hydrogen bond with themselves. They have O's, but they don't have OH's. They can hydrogen bond with water, but not with each other. It's only dipole to dipole attractions. So for one, they're not very reactive because oxygen has its 2 bonds. And for number 2, most of them in nature are small. And because they're not hydrogen bonding or ion to dipole attractions, simply dipolar, that makes them rather volatile, so they can evaporate quite easily if they're small. So what are some of the chemical properties of ethers? Well, if you saw this on an exam, right, what would you do? Well, water has to go in here somewhere and do something. This is all inert. So is this. So it has to go into the functional group, right? So what you're essentially doing is the reverse of reaction 13. You're hydrolyzing the ether under acidic conditions. And when it comes to oxidation, there's 2 things that could happen to an ether. Notice that in this case, using oxygen like that in brackets, not saying where the oxygen comes from, it's convenient because you see that you can put another oxygen between an oxygen and a carbon. When you do that, you get a peroxide. So the peroxides are already reactive, so whatever you use here has to be very reactive. You know, like chromate or permanganate or something strong like that. So what we need to do in this course is kind of understand, well, what do the functional groups do? When you take an organic chemistry course, it's like, how do I make the functional group do this? What fantastically reactive reagent do I have to do this with? But in biochemistry, we just need to know what the capabilities are. What can they do? Because everything is done by a biological process, not a chemical process in a test tube with fantastically reactive reagents. Another thing that can happen, if you were to see the X, then you want to form XH2. So what you're really doing is you're simply taking 2 hydrogens away. So now that carbon needs a new bond, that needs a new bond, so you let them have it, you get an epoxide. naming phenols, you should know that that's the phenol ring. They can form hydrogen bonds, right, with themselves, with water. And the unusual thing about phenols is that they're acids, weak acids. So I put it in water, I don't get a lot of phenoxide formed, but if I put it in sodium hydroxide, which is a much stronger base than water, then I can convert it all into the phenoxide. And it's stable, not because so much that it wants to really get rid of that hydrogen, but the reaction happens because when it does get rid of the hydrogen, there's ways to stabilize the phenoxide ion via resonance. So then I showed you the basic scenario of forming the hydroquinone, which you could call benzene diol if you wanted. And that can then act as an antioxidant, okay? Because when you form the semiquinone, there's resonance stabilization. When you form the quinone, there's also resonance stabilization, because this is a totally conjugated molecule. Double, single, double, single, double, single, double, single, get it? So in more complex molecules, they can act as antioxidants, like BHA, BHT, things like that. And we would have no way in this course to be able to predict what the products of that are. Just know that they absorb oxygen to protect your food. Just like how vitamin C absorbs electrons to protect your food from also being oxidized. So then with naming thiols, it's simply, in the most simple form, you're naming it not alcohol, but thiol. And then you might have to say, just like in alcohol, where is the SH group? So they're closely related because sulfur and oxygen are in the same group on the periodic table. The difference really is in physical properties. Thiols are completely nonpolar. So they don't do dipole-dipole, they don't do hydrogen bonding, only extremely weak abundance attractions. And so they can be quite volatile, and many of them actually smell. So chemical properties, you can form disulfides. So notice the difference between this reaction with thiols versus the same reaction with alcohols. With alcohols, you get an ether with one oxygen, but with thiols, you get a disulfide with two sulfurs. And we normally just call them disulfides. So any questions about this chapter? Okay. Chapter 24. Okay, so we looked at cis-trans isomers, right? In the cyclic alkanes, in alkenes, and those differ in shape, but they're not mirror images of one another. So they're stereoisomers, but they're not going to be mirror images of each other, so they are not enantiomers. What they are then is diastereomers. So what does it take to be an enantiomer? To have a mirror image, you have to be tetrahedral, and you have to have 4 different substituents. And those are called chiral carbons. Sometimes they say chiral carbons, chiral centers, chiral centers. So if I'm looking at this simple molecule, and it's because it was one of the first ones that its configuration was known versus its behavior in the polarimeter. So glyceraldehyde. So it's a common name. Here's the aldehyde group. You can see that it also has a hydroxy group. 2 of them. It's also a diol. Anyway, what carbon can be a chiral center? This one doesn't meet the criteria. It has only 3 different things on it. This one has 4 different things on it. One is the hydrogen, one is the hydroxy, one is that methanol type thing, and here is the aldehyde thing. So we have 4 different things bonded to it. And this is the Fischer structure that we'll be using. Here's the modified Fischer and slightly different, although this is really good actually. So what we do is we're looking at this carbon, that's going to be an X, right? So that blue carbon represents the middle X, right in the middle of that intersection of the 2 lines. Then the convention is that the most oxidized carbon, which is an aldehyde, goes on the top. And the CHO is how we designate the aldehyde. Notice that this is an alcohol. It's a primary alcohol. If I oxidize it one more step, that too would be an aldehyde. So this is more oxidized, so that's why it's on top. So then I put the other one on the bottom, right here. And then there's 2 ways to draw it. I can put the hydrogen on the left, and then hydroxy would have to be on the right, or I could have done it the other way. But when we draw this, that implies that the horizontal ones are coming out into your face. The vertical ones are going away from your face. And this shows you that pretty good depiction. So now that we know about D and L, so this one you can see is on the right, so that's D. Here it's on the left, so it's L. And don't forget that if I put the positive or the negative, that's an experimental parameter. It has nothing to do whether this is D or L. So here's the significance of having stereoisomers. Enzymes are also stereoisomers. So the surface is designed so that these binding sites, these attractive sites right here, will work and won't work with other molecules. Enzymes work with most enzymes almost entirely with only one substrate and nothing else. So L-glyceraldehyde is predominant in nature, and the D is not. Anyway. Or I got that reversed, sorry. So then if I gave you something like this, you would see that there's 2 chiral centers, right? So you would draw 2 chiral centers. Here's the 2 chiral carbons, right? Then the simple thing to do, these are not hydrogens. So you put them on the same side, draw its mirror image. Put them on opposite sides, draw its mirror image. And that's how you get the 4 stereoisomers for that type of a molecule. So if you are compound 1, you have 1 mirror image, and that's it. Enantiomers only come in pairs. So if you're number 1, you have you and your mirror image and nothing else. Other stereoisomers are not going to be mirror images. They're going to be diastereomers. And if you look at halfway in the molecule right here, this is not a mirror image of this. Same thing here, right? But in the case of a meso compound, this is the exact mirror image of this. So it cancels each other out. These 2, in fact, are superimposable, and they're the same compound. So if you are number 1, you do not have an enantiomer. And 3 and 4 are simply going to be diastereomers to you. Now, if you're compound number 3, you do have 1 enantiomer, but these 2 are the same, so you have only 1 diastereomer.
I have a question about that.
Yeah.
So if there's 2 chiral centers,
Mhm.
there's not always 4 enantiomers. Is that what you just said?
Well, the explanation is n, 2 to the n, right? So that gives you the maximum number.
Oh, the max. Okay.
Right. But here you have a degradation because of the internal mirror image. Does that answer your question?
Yes.
Oh, look, typo. Okay, so here's a couple more examples of that. And to tell you the truth, what I'm really doing here is getting you ready for the carbohydrates chapter. And amino acids are also either D or L, but in nature they're almost all L. And the polarimeter, I'm not going to give you explain how the polarimeter works. That's hopefully you learned from it, and that's good enough. I'm not going to ask you about the nature of light because that's more of a general chemistry type of question, or physics. But hopefully you understand what plain polarized light means. So if you're walking around outside with polarized sunglasses, what's coming to your eye is plain polarized light. So the reason sunglasses work so well is because to get to your eye right here, light has to be able to pass through those polarized transmission phases. So if the light is coming from an angle like here, it's not going to be able to pass through there. So what it does is it cuts out all that light rays coming from all different stuff, all the diffused light. And what comes directly to your eye is what's only being bounced off in a straight line from the object you're looking at to your eye. I have a friend who's a fisherman. He had these $200-something pair of sunglasses, and he told me that, oh, when I'm out fishing, looking into deep water, I can see the fish way down deep. And yeah, okay, well, maybe it's possible, but I couldn't see anything with them. I think he just had to justify having really expensive sunglasses. Okay. Okay, so any questions on chapter 24 then?
Can you you know when you're talking about oxidize, when we're doing the Fisher projection, it says the most oxidized goes on the top. Is it always aldehyde on the top, or does it really matter?
Well, we haven't really studied a lot of the functional groups yet, but let's see if I can draw like an amino acid for you.
Okay.
So here's a typical amino acid. Let's just draw something simple like so. This one is alanine. So alanine has the methyl group here, right? That's why it's alanine. If I change this to say this, for example, then that becomes serine. Make sense? So they're all like that. Okay. So how would I draw the Fisher projection? Here's my chiral center right here. So I'm going to draw it like this. Wait, I should draw it down here. Okay, so that's my chiral carbon right there. This is the most oxidized one, so I'm going to put it up here. Okay, and then if I'm going to make the carbons in a row like that, then the CH2 goes down here. So then I got those set already by the convention. So now I could put the H here and the amino group there. Or its mirror image would be this. Okay, so those two are enantiomers. This one is on the left, so this is L, oops. This is called L-serine. And this one is on the right, so this is called D-serine. But you see why this is the most oxidized carbon and why it's on the top? So that's just our convention. So you can imagine a group of people and they're all in the same room and they're trying to figure out how to draw something, and somebody has to say, well, why don't we all do it this way? So that was the convention. The most oxidized carbon, which is the carboxyl group, which you haven't studied yet, is going to be on the top. So if I had the same molecule, but come on, oops, how do I get that out of there? Oh, that doesn't show up. Okay. So now that one would be like this, right? And this would be CHO. That would be on the top. Make sense?
Yes, thank you.
So any other things you want me to go over? So I was looking at how to put the tests on the Laulima on that format, which I do with my other courses, but this course, I don't have anything ready to do that. And it would take me literally, I don't know, 10 hours or something to convert this onto that format. So yeah, it's not worth it. So that means I'll take the test. I made the test in Microsoft Office. I converted it to a PDF document. So as soon as you request the exam, I will put it into your Dropbox. And you download it, you open it, you print it. I doubt you'll be able to draw on it digitally. And then you have to, finish the exam, and then within 2 hours, take a picture of it or scan it or something and load it back up into Dropbox within 2 hours. So I did send out something. If you have a phone, the modern phones have scanners on it. Even if not, I don't know anybody who doesn't have a cell phone that can't take a picture. But you have to make sure that it's legible. So you need to do dark ink or something that shows up when you scan it. And that was the whole idea about that test quiz, just to see if you guys know how to do it. And anyway, I've never done it this way, but I thought we'd try and see what happens.
Can you go over the quiz questions?
The actual quiz question?
Yeah, the 1 and 2.
Okay.
You have like 5 minutes.
Let me see if I can remember where that is. Oh, okay, I found it. Share it. Maybe I should have done it on the iPad. Maybe what I should do is this. Can't have everything open all at the same time. Okay. I'm going to do it on the iPad now. I hope. Okay, so the first one is drawing the structure for trans-3-methyl 2-pentene. Okay, so pentene means 5 in a row, right? So 1, 2, 3, 4, 5. It's a double bond on the number 2 position. So here, I could have done it from over there as well. So that's 2-pentene. And then on the 1, 2, 3 position, there's a methyl group. Okay. So now I need to get it to look like the trans. Okay. So that means that if I have the methyl group up here, because that's a hydrogen, right? So there's the methyl on that carbon. There's the big one is the methyl group. On this carbon, the big one is the ethyl group. Okay, so that would be it. So it's trans because here's the big one on this carbon, here's the big one, and they're opposite to each other, right? I really wasn't meaning this to be an example to be studied with, but it's okay. So now when I add water with an asymmetrical reagent, I think of it like this. So this is big, this is small. So this is going to lead into here somewhere. Now, where is it easiest to get to? Well, here's a hydrogen. That's way smaller than a methyl group or a propyl group or anything else. So preferentially, the hydrogen will go to that carbon. Now, if you look at Markovnikov's rule, this carbon has 1 hydrogen. This carbon has 0 hydrogens. So the rich get richer, it's going to be this one. So here's where the hydrogen goes, and here's where the hydroxy group goes, preferentially. So this would be the major product. That make sense?
Yes, for like the one on the right where you have the OH on the bottom, if you put the OH where the methyl group is, would that be wrong because they're too close together, and so it would actually be like farther apart? Does that make sense?
You're talking about this one, right?
Yeah. So like the OH is on the bottom in the bottom position. Hypothetically, you have written it where the methyl group is instead of and flip those.
Oh,
Would that be
yeah,
wrong?
but it does not matter because don't forget, we're writing on a 2-dimensional surface, but the molecule itself is 3-dimensional.
Okay, I just wasn't sure if like because of the sizes, like they would repel each other and like be as far away from each other as possible, kind of.
No, all of these bond angles is the same. It's all
Okay.
109.5, right?
Right. Oh, true.
All of them. Yeah,
Okay.
yeah. I know it's hard to think like that.
Yep.
Yep, life is hard. Okay, so if you have other questions, you can always email me. Let me check the chat for a minute. Okay, gotta write something down here. Okay, so some student has another question, but I'll have to do that after, because I'm doing another review with another course right now at 1:30. But anyway, if you have more questions, just email, okay? You guys have a great day, and I hope you learned something.
Thank you.
You will
Bye.
save
Thank you.
banking in the future.
Thank you. Bye.
Take care.